All right, so let's start. Hello, everyone. Welcome to episode 37 of Warsaw Quantum Computing Group Meetup. Today, we have a pleasure to host Aleksandra Lipińska, and she will give a talk, Surface Code Design for Asymmetric Error Channels. Before we start, I would like to thank our strategic partners, Snart and Kogit, for supporting us, and our honorary partners who also help us in advertising this meetup. And yeah, I think that's all. So Ola, if you are ready, we can start. I just stopped sharing my slides, so the Zoom is yours. So thank you.
Thank you very much for having me here.
Yes. Okay.
I hope I can show you a bit about surface codes in general, as well as error correction and its use. There will be a few moments where I will be asking whether there are any questions. Then there can be questions given by microphone. Otherwise, it would be great if you had any questions, just write it in chat. I should be seeing it. All right.
Okay. And I can also try to interrupt if there are some urgent interesting questions. Yes. Okay.
Of course.
Good. All right.
Now, this presentation is based on joint work with Utkarsh Azad, Shilpa Mahata, Riju Sajava, Debashmita Bhaumik, and Ritajit Majumdar, which was done in part of the event Q Intern organized by QWorld. Now, the talk will consist of a few basic points. First of all, I will give a general introduction to quantum error correction and say what it's for and why it's important. Then I will introduce you to the stabilizer formalism on which surface codes are based. Later on, I will show you surface code, how it works, how it operates. And with surface code, a very important fact is what decoder you are using. And the decoder we are using in our work is the minimum weight perfect matching, which I will also introduce. I will give a very short introduction to the asymmetric noise model. And later on, I will show you what is our proposed surface code design. And finally, I will share with you our results of the experiments that we have performed. Now, the general motivation for quantum error correction, as many of you are for sure aware, is that quantum computers are very noisy machines. They are prone to noise from many different reasons, including noise on the gates, noise decoherence, etc. Here you can see a part of a table of mean single qubit error rates, which is how often does an error appear for a number of operations. And what we would expect to see here is something like 10 to the minus 12 to achieve good results. To be able to implement large-scale quantum algorithms, we would need something like 10 to the minus 14th. So right now, quantum computers, a good quantum machine is considered to have something like 10 to the minus third error rates. And as you can see, even the best IBM's machines achieve just definitely too little still. And this is what quantum error correction can help with. We can devise algorithms and structures that help us mitigate the noise and bring the error rate down. Now, quantum error correction is built on the big important foundation of classical error correction. And they have a very similar structure of what happens when And first of all, we have some information. It can be in any information. Theoretically, usually in classical error correction with bits. In quantum error correction, we have a state of a qubit. Then we have to encode it. Encoding is already the beginning of error correction, where we want to do something that later can help mitigate the effect of noise. After the encoding, we have the effect of noise. So for example, we perform our faulty operations. And later on, we have the decoding. So from this noise information that has been subjugated to noise, we want to decode it and have the original information again. For example, a very flagship comparison is the classical repetition code to quantum 3-qubit bit flip code. Now, in the classical case, for example, let's say on the left side of the screen, you can see an information which is just a simple string of bits, 0, 1. Then, when we do the encoding, we will repeat it. So introduce some information which is in a way unnecessary, because we will just copy the bit 3 times and just do the same with the second bit. This is the encoding. Later on, we have the effect of noise, which, let's say the penultimate bit is flipped. So from 1, we get 0. And later on, we want to get the decoding. And the decoder just sees this information. And what we can do is separate it again into the groups of 3s, and do something that is called majority voting. So for each group, we will see what appears most often. So in this first case, it's obvious it's a 0. So we decode it to 0. And in the second case, what appears most often is 1, which appears 2 out of 3 times. And then we again put all the three bits into 1 again. And hopefully we have achieved the original message. As you can see, it still is prone to failure when, for example, 2 of those bits would be flipped into 0, 0, 1. We would have a 1 instead of a 0 where we wanted. Now, similarly with quantum error correction, we have 3-qubit bit flip code. Now, something that is pretty important in quantum error correction is that there are a few crucial differences to how both states and error correction can function, which I will talk about in a moment. But first of all, we have a state, which is represented in the regular way. And then we introduce some redundancy again, similarly to the repetition code, where we change the zeros in the state to 3 zeros and 1 to 3 ones. So what we have to do physically is introduce 2 other qubits from 1 to 3. Then something might happen to the state. Now, this is a representation which is a bit simplified. There might be still more complicated ways an error might occur. The amplitudes might change a little bit, for example. But here, again, we would do something similar to what we did in the classical case. We would do majority voting. And similarly, we would arrive at the original message. Now, the crucial information differences, which I just talked about, are some curious properties of quantum states in general. Now, if we had an ideal quantum error correcting code, first of all, it should be able to correct many types of errors. Just like I told you a moment ago, we have different ways of workings on a quantum state. So for example, very important things in our work are things that are called bit flips and phase flips. Now, we can see in the previous example, a bit flip would be as if you applied an X operator or a bit flip operator on a qubit. But a phase flip, similarly, is when you would apply a Z operator on the qubit. But also, imagine a block sphere which, with a state on it. To create an error, you can move the arrow, let's say, or the point on the block sphere anywhere to the block sphere to another place. So this is how many different errors there are compared to just a classical bit flip. Now, similarly, if we were to move the dot that represents a state on a block sphere just a little bit, we should still be able to correct this error. And it's not particularly easy to do. Because of the no cloning theorem, we also cannot copy a qubit. So just like I told you with the classical repetition code, we cannot just take a qubit, look at it, and copy it or write the same state again. And we cannot do it because we would also destroy the superposition of a state. We cannot see what it is. So those are the crucial difficulties we have to overcome with quantum error correction. And now for the physicists, in here I will be using for the Pauli errors, the X, Y, and Z. This is the notation. And I have taken some liberties in general with the notation, which I will tell you about when the time comes. Now, I've told you about how to correct bit flips. For example, of course, there are many different codes, but for example, we can correct it by using the 3-qubit bit flip code. But how can we correct phase errors? So if we were applied to the Z operator. Now, we can do it by putting a Hadamard basis on our qubit. And the Hadamard basis is just when we apply the Hadamard operator, creating from the state, let's say alpha 0 plus beta 1, alpha plus beta minus. This is what would result. And now the property that is very sought after for us is that if you look at the result from applying the X operator on a plus and on a minus, it works just as a Z operator would on a 0. And similarly, the Z operator in the Hadamard basis would work as an X operator. So from this, it is pretty straightforward to come to the conclusion that we can just perform repetition code in this Hadamard basis and then come back to our regular basis if we want to by applying Hadamard again. Now, I've told you about 2 out of 3 possible Pauli errors and how to possibly correct them. But there is a fairly well-known property that we can express the Y gate in the means of the X gate and the Z gate, which means that we don't have to really worry about it. At least we don't do in this work. In general, there are many different noise models, and correspondingly, we also have many models for errors and how to correct them. But this is fairly, I would say the most well-known one is to just think about it in the means of Pauli errors. Now there is a very useful theorem. It is that if we can correct any T qubit, so T meaning the number of qubits, X, Y, Z, and I, and we know that identity we don't have to worry about because it is as if no error happened. And Y, I just told you that we also don't have to worry about it. So if we can correct X and Z errors, it will be able to correct basically almost all T-qubit errors. Why is that so? Well, you can think of it as a ways of the matrix representation. You can, on one qubit, an operator can be represented as a 2x2 matrix, and it would be able to be written as a linear combination of X and Z. And of course, the identity matrix, which is also fairly important. Now, something important is that the Pauli group, which is a group which is built upon the X, Y, and Z Pauli operators, it means that, first of all, well, the fact that it spans all of T-qubit errors is just the algebraic way of saying the previous theorem. But additionally, if we have any A and B Pauli errors, where A and B can be any X, Y, or Z operators, then those two operators definitely will either commute, meaning that A times B is equal to B times A, or it anti-commutes. So A times B equals minus B times A. This is a very important property in the stabilizer formalism, about which I will talk about now. So the stabilizer formalism is something very important to quantum error correction, upon which many quantum error correcting codes are built. Now, let's say I will show you this in the means of an example, and then maybe you can conjecture how in general it works. Well, already I have some notation that I would like to introduce. Is if we have an operator on just one qubit, I will be using this small notation. You will see why later on, but it might look unusual, and it is, but because some of you might be watching it on small screens, I think it is better to see that way than the usual notation of putting a hat over a letter of an operator. Now, if we have two qubits, A and B, let's say, and they are measured by operators XA, XB, where XA works on A and XB works on B, and similarly ZA and ZB. Those two operators are called stabilizers. And if we have operators on two different qubits, an interesting property which you can calculate on paper, the calculation is fairly straightforward, is that they will always commute. And this means that those operators will be compatible, meaning we can measure our state using both of those operators. Now consider the Bell basis of some state, 2-qubit state phi. If we calculate the eigenstates of those two operators, they will have the curious property that the +1 and -1, which will result, will be unique to each state of the Bell basis. So see that +1 doesn't repeat once, and similarly with each other state. So the combination of those two is very important. Now we can, if one of those qubits will be affected by one of the most important bit flip, so X, or a phase flip or a Z error, then the measurements will project the qubit state onto those eigenstates, and the measurement those eigenvalues will change. So to explain it maybe in more easier words, we can keep track of those eigenstates because they are classical in a way. So we can keep an, let's say, algorithm that stores those eigenstates. So let's say we have an error, which would be an X gate on the second qubit from the first state. Then we would result in 0, 1 plus 1, 0 divided by the square root of 2. So this is what we would see. We would not know what the original state was, but we did know the original state's eigenstates, which would be +1 and +1. And now if we measure our state currently, we will get -1 + 1. So we see that there has been a mistake of sorts. And similarly, we can do it with more complicated states as well, but this is an easy example, I would say. So are there any questions up until now?
Okay, do we have any questions? I don't see any questions on our chat, but maybe someone would like to unmute.
I can proceed if there are any questions. I can answer them.
Yes, let's go on. Mm-hmm.
Now the surface codes. If we are to solve a problem, so our problem will be to consider that there is some asymmetry in the noise. We need to consider two things. First, how will we encode our qubit? So the encoding doesn't necessarily have to be as simple as with the 3-qubit bit flip code. It might be more a bit more complicated. And the second one is the decoder. So the encoder and the decoder, basically. So with the encoding, we chose the surface code, which is a fairly popular right now way to encode our qubits. And how it works is that we put our qubits on a 2D lattice. And they have the property that is called the nearest neighbor. So they interact with the nearest neighbor of them. And now the notation, this is the surface code. The black dots with the numbers of them are something that is called the data qubits. And this is what the computation will be performed on. This is what we will concentrate on very much. The other are the ancilla qubits, which we don't have to worry about that much, but an important thing to note is that, first of all, they are there, and they are noted by those black small dots. And the squares, colored squares, are something called parity checks, or what syndrome measurement happens on. And this is where we get our eigenstates, similarly from the stabilizer. This is where stabilizer formalism comes in. Now, so the parity checks are the value of the measurement, which is determined by the state of those connected data qubits, so which interact with each other via the nearest neighbor. So now this is why I chose the notation I did. So we can get an X, let's say, error or a Z error on any of those small qubits. And for example, if we have an X error on the 0th qubit, we'll denote it by the small x0. The index corresponds with the index of the qubit. But now the parity checks are connected with the syndromes here, with the ancilla qubits, and they are operators on a few of other qubits. So let's go over this pretty quickly. X0 is this part right here. and it is an X operator on the 0th qubit and the X operator on the 1st qubit. Now, you might notice the half circles, and this is called the rotated surface code. We might also have just the square lattice, which would be the regular surface code. But on this surface code, it is fairly simple because of how small it is, and certain examples are well demonstrated. All right. Now, the surface code cycle. We have, again, the encoding, the effect of noise, and the decoding. I noticed a mistake, which is that with the Z errors here, there should be small z's, which I didn't notice before and correct. So it's easier than it might seem. If it is the big Z, it corresponds to small z errors. Now, let's go back to the surface code cycle. First of all those syndrome qubits or ancilla qubits will be initialized in their ground state. So let's say 0, and will be entangled with the neighboring data qubit using the NOT gate. Then we will perform the error syndrome measurement so that we know those eigenvalues. And then finally, there will be the effect of noise. And we will perform the error syndrome measurement again. And we will be able to say whether the value we've got is different or the same. If it's different, then we have to detect what errors we had. We had to do the decoding. That's the basics of it. Now I will attempt to draw something. So how would the encoding in general, or rather the error measurement, work? Now, if we have a surface code, now I will not draw the dots, but you can think that the data qubits are on the points of crossing the lines here. So we have the 9 data qubits. It's similar to this one. So let's say that we have an error on our 4th qubit here. We don't know that as we're doing the program, but let's say that we can somehow inquire into this. And this is what happened. Then after the syndrome error measurement, I will explain maybe some difficult to understand weird qualities of surface code. Now, first of all, maybe I will say it first. Now, if we have the z's here, they correspond to whether there has been an error of the X type. And if we have the X, it corresponds to whether there has been an error of a Z type. I know it might be confusing. And the second thing that is confusing, maybe, is that we will get -1 or +1, depending on whether there has been a problem detected or not. And the +1 and -1 does not correspond to the eigenvalues. It corresponds to a change in the eigenvalues. So this is what we would get. Now let's go over what this means. So this in general means that we have a detection event triggered on this square and this square. And no detection event took place on any other squares. But we know that it is flipped in a way. So we have a Z syndrome, which means that we had an X error or a bit flip on this bit 4 here. This is how it works in general. Now, there is also something that is important to note, is that we have something called the logical operators, which isn't particularly difficult, but is very crucial to understanding where surface code might fall short. So, for example, if we have a logical operator that goes all the way through the surface code, it is called a logical operator. In this case, it would be the logical Z operator. And it also denotes something that is an important measure of quantum error correction, which is distance. In this case, it would have distance 3. So this code presented here would have distance 3 by 3. This is the notation that I will use, 3 by 3. So this is what is important so far to understand about the basics of surface code. So how it works, it's based on the stabilizer formalism. The stabilizer formalism helps us with detecting errors, where we sort of go around being able to see the state at any given time. We are not able to see the state, but we are able to see the eigenvalues, which are measured by special operators. And again, important thing to note is that the letters are in a way flipped. So the letter Z corresponds to an X error that would have happened, and vice versa. Now let's go back to the presentation. So that's what I've already told you about, that we have the logical operators. They will be denoted by X, L, and ZL respectively. And they are operators that are spanning the whole length of the surface code. And those operators will have the length which is greater or equal to the distance. Distance is defined in many different ways. I've told you how you can look at it in terms of surface code, which will be the important thing. Another important quality is that if we have T errors that a surface code can correct, and it is determined by the distance that I've just told you about, and it would be the floor of D minus 1 divided by 2. Now, two other important measures is the threshold value and the pseudo-threshold value, which will be important with our experiments later on. Now, the threshold value is the intersection of the logical error rate for different code distances. We use it when we have one family of surface code designs and we want to compare them in general. So again, if we are checking the logical errors, how often they occur, if we graph it, then when we have two different, let's say, surface code designs, and they cross the point of the crossing, when one surface code design, for example, is more efficient than the other one, this would be the threshold value. Now, the pseudo threshold value, which one might argue is the more important one, is if we graph the line where the physical error rate is equal to the logical error rate, where it should have been important to mention that the logical error rate is how often there is a logical error, which is defined as an error on a logical operator. So spanning the whole length of surface code. Now, the point where in these terms, the physical error rate is equal to the logical error rate. If our surface code design is below that, that means it's pretty useless to use it in general. But if it crosses this line, so it's better, then this means that we should employ it, or there is some increase in performance. And this will determine the highest probability of a physical error, well, below which we shouldn't use that code in general. Now, our decoder. For those of you that come from a computer science background, you might be acquainted with graph theory, which is very useful in surface codes in general. And you might also be acquainted with at least one of the parts of minimum weight and perfect matching, namely either minimum weight or perfect matching. And it might be difficult to understand it. I will draw it for you later on to show you two examples maybe of how it works and when it doesn't. So again, what we will see is we won't see where an error has occurred. We won't see that at all. We will just see a measurement of a -1 state. So let's say we see it on those 2 points. And then somehow, from those measurements, we want to be able to tell where exactly the error occurred. So on which of those numbered dots there was an error. And this is where graph theory comes in. Now, first of all, we will want to map something called dummy nodes, which are highlighted here in gray. Then we want to use the notion of a perfect matching. First of all, maybe say, we want to employ checkers rules, which is we can jump from each of those noted, labeled in green syndrome measurements over a qubit onto another qubit or a boundary node. So we can jump over, for example, from this syndrome measurement over 4 onto this syndrome measurement. But we cannot go over when there is no qubit. So this is these are the rules, and we draw or graph each possible of those sort of jumps. And we will have a graph. And each of those single jumps will have length 1. And then we will graph all the possibilities. Now we want to find a subgraph where each vertex is an error syndrome, where the total weight will be minimal, which will be the minimum weight. And to do this, we'll do something called the perfect matching, which is where each vertex can have at most 1 edge connected to it. So we want to find such a subgraph, which has the minimum total weight. And for example, here, in this case, what it guessed is, imagine that from here we would jump over qubit 6 onto a dummy node. And from this one, we would jump onto 8. The total weight would be 2 jumps, so 2, which is the minimum weight. And now the qubits that we have jumped over on the subgraph would get marked. And this is where we would guess that our errors have occurred. Now, allow me to draw maybe 2 examples. So, for example, let's say that we have gotten -1 here and here. Now, we will mark also in red the syndrome measurements. Okay, so maybe I will remove the -1s. And now, let's see what we can jump over. So we can jump over, here will be, let me draw maybe the dummy nodes. Okay. We can jump here as well as through this qubit here, through this qubit here. Now we would assign the weight 1 to each of those. Notice that we jumped through 2 of the syndromes. So this would be 1, this would be 1, and this would be 2. Now the minimum, let's say pink, the minimum weight, perfect matching, in this case, would be this one. Because each vertex is, in a way, accounted for. And this is the resulting subgraph. Now, this jump corresponds to a jump over the 3rd qubit in our notation, which is what we would mark that happened. And if you remember the example that I have drawn here, this is exactly what did happen. And in this case, the decoder worked correctly. So we had given just the syndrome measurement results, and we conjectured from it what qubit the error happened on. Now I will show you an example of where that does not work. And all ways of encoding our qubits, because of the limitations, will have some faults and will not work in some ways. So the fact that it will not work in some example, that does not mean that it does not have its usefulness. but still, it's very useful to be aware of those misgivings. For example, let's say that error measurements yield those two results. I have in mind some qubits that it worked on. You can think about possibilities of where an error has happened. So now, what can we jump over? For example, we can jump over this qubit here, the 4th qubit, just as well as the 8th qubit, creating this sort of line. Similarly, we can jump to the boundary node over the 1st qubit or to another boundary node over the 7th qubit. Now, this is the graph that we have here. Each of those has length 1, each of those little parts. Now, our algorithm would deduce the minimum weight perfect matching, as you might have already guessed, is again one of length 1. So you can already see how it's biased towards choosing one line over 2. We could choose, for example, this line and this. It would also be a perfect matching, but it would have not a minimum weight in total. Why we chose, why it is that way? It is because in general, it is more likely that one error has occurred than 2 errors. And this is why it chooses the minimum weight always. But what error happened in reality, or let's say what I had in mind, was an error on qubit 1 and an error on qubit 7. Both were X errors. So you might see how if we had an error on those 2 qubits, which was the X error, then the one that is neighboring, the syndrome measurement which is neighboring to this qubit is this one. And this is why it would have an error measurement -1. And similarly, one which is the most close to this qubit, the nearest neighbor, so to speak, is this syndrome here, which is why it would yield -1 as well. But also, if an error has only occurred on qubit 4, it would yield the same results because of the nearest neighbor with those 2 syndrome measurements. So if you do not understand something about this or in surface codes in general, I would say it would be useful for now to ask, and I would be very happy to receive any questions. Because later on, we will use this knowledge.
All right. Do we have any questions now? I don't see any questions.
Okay, then we can proceed. And the third final big part of the presentation. So let's say, first of all, the short motivation. The motivation of our work. It is that here you see phase errors happen more often than bit flip errors. So Z errors happen more often than X ones. And we can characterize the level of noise, or rather the parts of the inner happenings of the noise channel by two parameters. First is called the relaxation time, and second, it is the dephasing times. Both are just like portions of time that it takes to do an operation on a quantum computer. Now, dephasing time, during the dephasing time, we only are able to receive phase slip errors. I will not go into the specifics because I'm not a physicist and I would not be able to tell you in depth about what it exactly means, but this is the fact that during the phasing, we just are able to notice phase slip errors. While during the relaxation time, we are able to notice both phase slip errors and bit flips in a similar to 50-50 then, which is what the asymmetry results from. And we have a quite a large asymmetry tending towards those phase slip errors, so they will happen much more often. That's basically it. So in many noise models and in many quantum computers in real life, phase errors happen more often than bit flips. That's all we need to know. And now what we want to do with it is we want to find a solution or a way of encoding our qubits and decoding this way of doing our surface code. Okay, we have a question.
Yes, there is a question. What's the extra qubit is required to correct the error or n qubit in surface error correction code?
I'm not sure I understand the question.
So maybe, Dev, maybe you could unmute yourself and ask the question.
I will go back to here we have it.
Mm-hmm.
You can also write on the chat if you don't want to.
Yeah, feel free to unmute yourself. I believe that it will be the easiest option. I just ask. Okay, so repetition code. Yes, go on. Mm-hmm.
Yes, repetition code is generally 3n code, but it doesn't necessarily have to be. It's the easiest because majority voting happens so easily. We have 2/1, but in reality, we will have much bigger encodings. So just like in surface code, this is the easiest example we could have, easiest non-trivial example. But in reality, we would still have many different qubits encoding one logical qubit, one big qubit. So this is why we chose it that way. It does not mean that we have this. We chose 3s because they're also the easiest example in the 3-qubit repetition code, but in terms of the surface code, it is 9 here because it's the easiest as well. It can be bigger, right? So in the classical quantum surface code, it would be a square lattice always, so n by n. But other than that, there are no limitations other than the resources that it takes to generate those qubits. I hope I helped answer your question. Okay, great. Thank you very much for the question, by the way. Now, our proposed surface code design. During one of the previous presentations, one person asked before we got to this part, why couldn't we just make a rectangle out of a square? And this was a very good question because basically this is exactly what we did. So you can understand it in the easiest way that we just simply made a rectangle, where now instead of the x by x, we would have some x by y, let's say. So it would be here, the logical x would be of length 3, of distance 3, and the logical z would be of distance 5. Now, the general idea is fairly simple. We would have in these terms, dx by dz surface code. Now, according to the equality that I've already presented, we could, in this case, correct dx minus 1 divided by 2 and floor of all of that, tx errors. So we could correct this many bit flips, and dz minus 1 divided by 2 and floor of that, phase flip errors. So now we have this difference. And this is the basic example where in theory, we would be able to correct 1 bit flip error for every 2 phase flip errors. So this is the example that will take place prominently in our results. So in total, we would have 8 X stabilizers. So one they detect Z errors, and 6 Z stabilizers. So the ones that will detect X errors. So note how there is more X stabilizers than Z stabilizers. And they will be able to correct, just as I mentioned, 1 bit flip and 2 phase flip errors in theory. Now, some qualities which also might maybe interest physicists more is that they have 2 to the power of dx times z degrees of freedom, and a similar number, but dx times dz minus 1 is the power degrees of constraint. All right, now the logical operators and logical errors. What you might notice is that if we look at the logical X operators, there will be more of them, quite a lot of more of them, than the logical Z operators. We'll have just 3 logical Z operators, while we'll have 5 logical X operators. They are listed here down below. It retains the very similar, exactly the same actually, way of presenting it just as it was in the regular surface code. So let's take qubit 6 in this case. So for example, if we take Z stabilizers, Z1 and Z2 is one that they correspond to the 6th qubit, which is again the nearest neighbor property. Now, of course, just as I showed you before, our decoder might make a mistake. And then it is very dangerous, because throughout the whole running of the program with many different operations, this error will persist and it might create many more errors. Now here we can notice something that will be useful later, that logical errors, logical X errors in here might be very dangerous because there's so many of them, and we just need 3 qubits to happen on for them to fail. And logical errors we are not able to correct them. If you were to look at what would happen, let's say to Z1 and Z0 with this logical operator, if all 3 operators encountered a X error, so 0, 5, and 10, all of them, this syndrome measurement would first yield -1 after it detected the X error on qubit 0, but then it would flip again because it detected error on qubit 5. And similarly, with Z0, we would notice a change. I mean, we wouldn't because of how it works, we won't notice a change to -1 and then +1. We'll just notice +1 consistently. So we have both 5 and 10, and they would result in having +1. So we would think that nothing has changed, while in practice, we would have 3 errors, which is very, very dangerous. Now, our results. I will not get into the methodology too much, but we have created results of encoding some surface code designs, running some running some code where a number of errors happened, and comparing them in a myriad different ways. Now, here might be a useful moment to show you again how a pseudo threshold works. And it works, those are the graphs, which graph on the x-axis the physical error rate. So simply how many errors we encounter for a number of operations, and logical error rate. So how often we have this logical error when a whole line of the surface code is affected. Now the red dotted line is the line where the physical error rate is equal to the logical error rate. And important thing to note that the orange line is our proposed surface code design. And both the blue one, which represents the 3x3 code, which I showed you earlier, and the green line, which is the 5x5 code, which I did not show you earlier, but it's just a lattice of 5x5 qubits. So we are looking at the performance of the orange line against the green one and the blue line. And this is the performance. First of all, the upper one we can look at, and it's a performance for correcting phase flip errors. So the ones that we want to look out against because of the asymmetry of noise. Now look how early the orange line crosses the logical error equal physical error line, so the dotted red line. It crosses it very fast. It corresponds to this pseudo threshold here. And compared to that, it's very early on that we see the same behavior in both the symmetrical codes. This is a very good sign. It means that our code is working as intended. And here is the performance in terms of bit flip errors. Now we notice something strange at first glance. It's that our orange line performs considerably worse than both the symmetrical codes. And it is because of the sheer number of possible logical errors that might happen. There's so many of them, and they're also fairly short. So notice that if we had the regular 3x3 code, we'll just have 3 compared to the 5 of the possible logical errors here. But if we have the 5x5 code, it also will have the 5 possible logical errors, X errors, but they will be considerably longer. We would have to have an error on all 5 qubits in a line for it to not work. So this is why this performance is worse. But also, we have not checked what will happen in general when we have an asymmetry of noise. This is just splitting it into 2 groups of performance on the phase flip errors and bit flip errors. Now, some numerical results. again, you can see here the variation of the pseudo threshold, which is something that we will observe in a moment. We have our asymmetrical code here in the middle, and the symmetrical ones on the sides. And marked in red is the moment after which, well, the number here is the asymmetry. So when we are going down the list, the asymmetry increases. Now, at one point, which is marked by the red color, we see a plateau happen where we see the decrease again of the number of errors. And here we see it. We see that our asymmetrical code happens in the furthest point possible. I will show you the graph of it later, but just to know, this is a good sign that this happened. We want it to be as far down the line as possible. There might be some variations, but we have done enough experiments where we do see this tendency with the numerical results. The other interesting part would be the variation in the threshold values with respect to asymmetry. Now, we can see it, the threshold moving to the 0.5 part of the graph as the asymmetry increases up to the infinity, where infinity would be infinitely many phase errors compared to just X errors. I would not be able to tell you whether it is so much a good sign or a bad sign, but it is interesting to note. Now, arguably one of the most, if not the most important graphics in our paper is this graph right here, which corresponds to here, those numerical results on the left. Now, the asymmetry of noise here is happening on the x-axis. On the right, we have tending into the infinity. So here would be the symmetry. So the total symmetric, one bit flip for one phase flip. And here we have all the phase flip errors. And on a-axis, we have the pseudo threshold. So at what point does the pseudo threshold happen? So it's a bit different than the original pseudo threshold that we've noticed here, where the pseudo threshold is a point on the x-axis. Now, let's notice what happens when we have a very small asymmetry. First of all, important thing to note is that the symmetric surface codes are bundled up down here. And the asymmetric codes are all over here. So let's say brownish color, the red one and the dark blue one are the symmetric ones, going from 3 by 3 to 7 by 7. And we have a different asymmetry of asymmetric surface codes, which constitute the rest of the graph. When we have this small asymmetry of noise, we can see that the symmetric codes perform better. But as we cross a sort of threshold, which is not either the threshold or the pseudo threshold, by the way, but I'm just talking as we cross some point of asymmetry, we notice the asymmetric codes showed up much further up. And it is fairly early in the asymmetry, which is about 5, that this change happens. And all the while later on, we see them remain down here, while those codes split up, which will be important for final remarks. But they will go all the way up to here. But And what we can see, it might be expected. As we are going up, the code which is the most asymmetric will have the best results. But of course, in reality, we won't have the close to infinity number of asymmetry. We will just be going somewhere around here, when we have a real life model. So it is important to choose which point of asymmetry we want to choose. And it's doubly important because of the big distance in the pseudo threshold value that you can see in between those different codes. Notice how the symmetric ones, after a point, they are very close together relatively. But the ones that are asymmetric are very split up. And that's why it's very important to know what level of asymmetry you have in your noise model and be able to choose your code, asymmetric surface code, accordingly. So this is what this would be about. Now, to summarize, our proposed surface code design takes the square lattice, that is the classical surface codes, makes a rectangle out of it with the distance dx by dy. And it will be capable of correcting more phase flip errors than bit flip errors when we have asymmetric noise. Now we have performed some experiments which compared the values of the pseudo threshold, which compared the asymmetric codes to the symmetrical codes, and as well performance in case of X errors and Z errors with different degrees of asymmetry. And in every single case of different levels of asymmetry, the asymmetric comes after a point provided to be much better and have a much better pseudo threshold and threshold values. But there is a caveat of having the logical X errors happen much more often. So we need to be sure that we do have this asymmetry of noise when we are going to be using the asymmetrical codes. And of course, it will be fairly simple to apply this model to the inverse case of the noise model. So if we have bit flips more often than the phase flips, we just flip the distance dx and dy, and we should achieve similarly good results. So now for the time when hopefully there are some questions. This is the quantum error correction sonnet by a prominent scientist in the field of quantum error correction, David Gottesman, which concludes many different things which we have talked about in terms of quantum error correction. So are there any questions?
All right, thanks Ola. Very nice sonnet, by the way. Quite interesting and funny. All right, do we have any questions to Ola? This is the last chance. Okay, so maybe I will ask one question. So how do you think, because you've been already working in this area for some time, how do you think, what might be the future of this area of quantum error correction in general, or the surface codes in particular? What I mean is, how do you think? Do you think that, let's say, within the next 5-10 years, we may expect that these quantum error correction methods will lead us to significantly better quantum technology than quantum computers than we have now, or maybe we can do some other predictions? How do you think?
I am not able, of course, to give a definite answer, but it is a very interesting question. And I think that, well, it is quite hard to conceive good algorithms and good structures for quantum error correction. So I would not expect something in terms of the 10 to the minus 14th error rate that is needed for large-scale solutions. So I do not think that quantum error correction will solve all quantum computers problems, but it is a very lively field right now. There is a lot of happening. If you look at how many new papers are written every month on the topic, there is a lot, and I think that there is still considerable room for improvement. So I think we can expect a fairly good amount of better performance, but maybe not in terms of classical computers.
Okay, good, thanks. All right, do we have more questions? Okay. There are no more questions, so let me, okay, so before I stop recording, let me maybe share my screen once again for a while. So I just would like to introduce our next meetup. Just give me a second.
Well, thank you very much for having me at any rate. It was very nice to finally to be here after watching the seminar for some time.
Thank you, Ola. So just give me a second. I will just. All right. So first of all, Ola, thank you also. So first of all, for accepting our invitation and very interesting talk. So as usually, the recording will be available on our YouTube channel, hopefully. So I will also later send a survey, a feedback form. So you could share your opinion on this lecture. We would also like to thank once again our strategic partners, Narto Kogit, our honorary partners, and we would like to invite you to join our next meeting. And it will be in 2 weeks from now. Oskar Słowik, also member of Poland, will give a talk. He hasn't sent me the title. I know that he wanted to change the topic recently, so we'll see. We'll announce this meetup soon. Most likely this week or at the end of next week. So stay tuned. Feel free to join our mailing lists, Facebook group, follow our fan page, YouTube channel, Twitter profile, LinkedIn profile, and so on. And we hope to see all of you on our next meetings. And Ola, once again, thanks for a great presentation and also answering all the questions that we had.
Thank you very much.
Great, I just stopped recording and I've also stopped sharing. So thanks once again, everyone. Have a good evening or day, dependently on where you are, and have a good week ahead. Hope to see you next time. Bye-bye.
Thank you, bye.